Okay, hello, welcome everyone. This next talk will be presented by Jordi Gutiérrez Hermoso. Welcome. Tell us.
Right. So this is a talk about video games, and it's about playing video games fast. This is called speedrunning, and the point in speedrunning is to get to the end. Is to get to the end of the game fast. The end of the game can mean different things, but the point is to finish the whole game as fast as you can. That's speedrunning. It's a spectator sport. People stream their videos on Twitch, although they also record the videos and put them on YouTube. People like watching speedruns. It's because it's fun to watch, especially if you've played the games. It's kind of like the video game Olympics, except it's always running. People are always playing video games and trying to play them as fast as they can. It's a lot of fun to watch. It's serious business. There are online leaderboards where people put up their best times and they compete with each other. Speedrun.com and Speeddemo's Archive are the two most popular boards, probably. And there are also live performances. There's Games Done Quick, which is happens a couple times a year. A lot of people get together and have a conference very much like this one and play video games very fast. There's also the European Speedrunner Assembly, which happens in Europe. They're very similar structured events. So here's what an event looks like on the top left. They're playing Super Mario Kart 64 very quickly. On the bottom right, it's a pre-recorded video. It's a little trick in an old game called Metroid. They're performing a trick there to skip most of the game so they can get to the ending faster. If you want to know, I'll tell you what that is. Performances are very interesting and the audience goes wild. For example, here's someone playing a game one-handed. They're holding a Pokemon with the right hand while they play the game with the left hand. So they're playing with just one hand. Here's someone playing a whole game blindfolded. They played the game so much that they memorized it and they know exactly what to do all the time. My slides are a little off, but I hope you can see them correctly. They were fine on my computer. But what if you want to go even faster than what humans can? That's called a tool-assisted speedrun, a TAS. So with a tool-assisted speedrun, a machine is playing the game, and the humans program that machine to play the game. All the button presses are pre-recorded. You pretty much record what a perfect play of the game is, and by some method, you make the video game console play this game perfectly. It's fun to watch as well because machines can do things that humans can't do. If you want to see what a perfect play of a game looks like, that's what a TAS does. It's also serious business. In order to perform a task, you have to have a lot of knowledge of hardware and software of the machine you're working on. And people also work worldwide together to make task records. They share knowledge and they understand how the machine works. Up there on the top left is TaskBot. He's a little robot that plays video games very, very quickly. And in order to program TaskBot, there's a lot of knowledge involved. You have to know how the software works, how the hardware works. It's real serious engineering to create a task. Now, but a task, where does the task run? A lot of these games are old video games. We like old video games because we studied them a lot. We grew up with them. They're fun games. But there are two ways to do it. One's an emulator. On an emulator, that's an application running on your PC that's pretending to be the old console. You're not playing on the old console. You're playing on an emulator that's pretending to be the old console. Nintendo even releases versions of these newer. They releases nostalgic versions, but they're just emulators running on newer hardware. It's not the original hardware. Well, the advantage of an emulator is that the task developer has a lot of tools to create a task. It's software development. This here is like a full IDE you can use to create your tasks. You have tools to create. That's why it's called a tool-assisted speedrun. But people want to see what's this like for real. The emulators are fun, but we want to see what it's like on the real hardware. And there are a lot of enthusiasts, myself included, who still collect the old hardware. You know, it's like playing on the old vinyl. You want to have the old machine and you want to see what it's like if you could actually run this perfect gameplay on the old machine. So to do this, the task developer has to somehow connect the tasks to the old hardware. And then you play like it's 1991 in 2025. To do this, you have to be an electrical engineer. You have to wire the little robot. Okay, to be fair, the little robot is just to make it look cute. What you really got to do is you have to wire a chip to the machine. You have to wire a machine somehow. You have to use a breadboard. You have to solder things. You have to know what you're doing electronically. You have to become a little bit of an engineer to do this. And once you've done this, will it actually work? That's the question. Because you've been working on an emulator. You developed your tasks in an emulator. But the emulator is not the real thing. The real console has quirks that the emulator might not be able to emulate correctly yet. In that case, well, the speedrun enthusiasts really want to see, could I actually make my dinky old machine from 30 years ago run this game perfectly? Can that happen? That's the real question here. And this whole story is about video games, but it's about a particular video game console, the SNES, also called the Super Famicom. It wasn't very popular in Europe, although it was here. I think Europe at the time had other consoles that were more popular. But the SNES is a computer. And this is what it looks like on the inside. It's got chips, it's got capacitors, it's got resistors, it's got connectors. It's a real computer. Some of these chips do graphics, some of the chips do sound, some of the chips do processing. It's an interesting architecture. And this story is about one of these components, which is this little thing here. This little part forms part of the audio system of the SNES. It's a ceramic resistor. Basically, it keeps time. If you have like an old wristwatch that's electronic, or a microwave, those use quartz oscillators, which are a bit more precise, but a bit more expensive. In order to save costs for the SNES, they use the ceramic resistor, which is a little less precise. And we suspect it's aging in some way. And that's what this story is about. That ceramic resistor, which controls the speed of the sound chip, also controls the overall behavior of the machine, because some games use sound to time certain things. Certain events depend on the sound, on the sound system of the game. So the problem was, we are making TASs work on the original hardware, but because of that sound chip not going at the right speed, our TASs are going out of sync. And suddenly the button presses don't make any sense, and the game doesn't work as it's supposed to. There are two examples. Speedy Gonzales is one game. The poor mouse is dying because the TAS isn't working. And Donkey Kong Country 2. Diddy Kong and Dixie Kong are dying because the TAS isn't working. So we want to know what's happening here. This little ceramic resistor isn't working correctly, and we want to know why. So we got to put on our deerstalker hats and figure out what's going on. For that, we need data. So in order to gather the data, engineer Litnerick, he's a community member. He wrote a program that runs on the SNES that measures the speed of the sound system, the digital sound processing at the very bottom. Nominally, it should be 32 kilohertz. On this particular instance, you can see that's actually 32.06 kilohertz. It's running slightly faster than the spec. And we want to know, well, how bad is this effect in general? In order to do that, another community member, Duango AC, he went on the internet and said, hey, people, we need data. Grab your old machines, run this program on it, and tell us how fast is the sound system working. In order to do this, we used two major tools. Duango used Nextcloud to gather the data, and I helped Duango AC use Grist to interpret the data. And we worked. I mean, first he gathered the data, he already had it, and he came to me and said, well, what can we do with this? And I said, we're going to use Grist. So let's see how this worked. So Duango put up a little form. There's a little QR code there you can scan for the live version of this form if you want to see what it looks like live. So he puts up the form, and then people send data, and they take screenshots of their machines. They run the little program on their machines, and they measure the data. Here you can see there's several different readings, and then they submit on the form, and we get it here. It's very nice. We have all of these measurements of the speed. They're all around 32 kilohertz with quite a bit of variation. Not in absolute terms, but in relative terms, there's a lot of variation. Okay, so why Nextcloud? I just want to advertise here Nextcloud a little. It's great for file synchronization. It's basically your private Google Cloud, Google Dropbox, whatever. It's for sharing files. That's the main purpose of Nextcloud. But it's also good if you want to do something like this. You put up the form and people send you data. It's self-hosted and open source, which we all love. It's for public file hosting. You can do data gathering with it. Another thing it does is it has very fine access controls. So if you want to, for this project, Duango AC gave me access to the actual real data, and so I could work on it. So he gave me access to on Nextcloud, which was quite convenient. Next, I came in and I started using Grist for this purpose, for analyzing the data. So the thing to do is Grist is basically a SQLite database with with a web interface on top. So I gathered all of the data into several SQLite tables, and I put them into Grist. This is all self-hosted as well. There's a little QR code you can scan there if you want to see what this looks live, the Grist version of this. So the first thing we noticed is this is the data that we got. Every red dot here is, so the experiment was this. We told users to run their SNES and wait for it to warm up and give us the measurement when it was cold and then when it was hot. The blue dots are the speed of the oscillator when it's cold. The red dots are when it's warm. And they're aligned vertically. So it says every vertical line is one console. And we can see here it's obvious that every console got faster as it warmed up. I mean, we didn't have a single one that didn't. Then I plotted the warm frequencies and the cold frequencies. They're very close to normal. These are the histograms of the data. This is all being plotted in Grist. This is an experiment that we run for a single console. We took a single console, we froze it, like put it in the freezer, literally. Took it out of the freezer, and then measured the frequency of the sound chip along the temperature. This gave us that the temperature and the frequency are almost perfectly correlated. Like it's almost the same curve. Of course, the temperature has fewer data points, so that's why it looks like a staircase. By the way, there are newer features. We could have used forms in Grist as well, but at the time when we ran this experiment, Grist didn't have forms yet. But you could also use forms to submit the data and do everything in Grist. We might do that next time, but there are advantages of using both Grist and Nextcloud in this case. So again, why Grist for this whole thing? Well, Grist is a web-based spreadsheet on a SQL database. It's self-hosted open source, as before. We love that. I think it has pretty good visualizations. You can do lots of things. All those charts that I did were made in Grist. The nice thing also is that I had to clean up a little bit of data, like for the experiment on the single console, where the data shows that the temperature is rising along with the speed. The temperature was a little bit noisy. It had a lot of oscillations. So I just took a 5-point moving average to smooth it a little, which I think is reasonable because the measurements were like every second or something like that. It was very fast. Grist also has structured data because it's a serial database. Every column is only one type. So there's like you can't mix dates with frequencies. They're different types. Okay. From this, we got some clear conclusions. One is that the distribution of clock speeds is almost exactly Gaussian. It's not as easy to watch. Seeing those, I ran what's it called? The Wilcoxon. Sorry, I did run the stats test. It passed. It's pretty much exactly Gaussian. Every console got slightly faster as temperature increased. That was also obvious. And there is more variability between consoles than within a single console. So, like, if you want to try to get it more precise, don't change the console you're working on. Set it to a particular temperature and try to work with that temperature. But the problem is, this is hardware that is almost 30 years old. I think it's like 35 by now. The SNES is a pretty old system, maybe older than some people in here. So is the clock speed of the SMP chip, that's the sound chip, is the clock speed changing as the console ages? We don't know, because we just ran this point. We just ran the experiment now. We don't have data from 30 years ago, someone running this experiment to see how fast the chip is. How much does impact does it have in humans? So the sound chip actually is actually creating the sound. There are humans that can hear the 60 hertz difference out of 32 kilohertz. They do exist. I can't hear it myself because I'm too old. You lose hearing when you get older. But there are people that can hear the difference. But the point is more for the gameplay, because the sound chip actually times certain actions in the game. Does this affect humans? So far, we haven't seen it affect humans. It only affects the tasks. And the last question is, could we modify the hardware to allow console verification of the task? Maybe what we'd really need is a special SNES with a specific sound chip that is fixed at a specific speed. Maybe people will find that acceptable. Maybe think, okay, fine, you can't verify the task on the real hardware. What if you modify the hardware a little? That's probably the only thing that we got to actually do to make the task work on SNES. That's my talk. Thank you.